Okay, so now let's just quickly make our mesh in gmsh or 3D mesh. So let's just define a new file here, sphere.geo. All right, let me just increase the let me just zoom it a bit more. Okay, so right, so now this should be visible. So let's start off. So first we have to just add our sphere. So just select sphere and we just put the radius as 1, add, radius is 12, add as well. So now we have our two spheres here. So now we just have to take the difference. So we go to the booleans, right? So inside booleans you can do intersection, union, difference and so on. So we'll just go for the difference, and we have to select an object and a tool. So basically it's just a minus b. So object is your a, tool is your b, so b just gets subtracted from a. So that's what we are going to do. So let's just Alright, so I'll just do this in a script because it's slightly difficult to see this in the GUI. So let's just go to edit script. So here I have selected the surface, so there's no point in really subtracting the surfaces. We have to subtract the volumes. So that's it. So now we have our difference. So let's just reload the script, and we can just now start the meshing. So let's go to mesh. Let's ensure that everything is correct. So this is your algorithm in 3D, which is your Delaunay. So this is correct. So for 2D you really have a quad mesh. So this is wrong because we would get quads. So we want triangles. So let's do frontal Delaunay. And here you have an recombination algorithm. So let's so we don't want quads here, so we'll just uncheck the recombine as well. We are going to use linear elements, so just put this as 1. Okay, so now we can just mesh this as 3D, right? So this has created the 3D mesh. All right, so this is our 3D mesh, and let us have a look at how it. So these are your outer elements, your outer triangles, and this is your inner, right? So you can see there are these nice tetrahedrons inside. So this is our mesh, and now of course we'll have to refine it a bit, but first let's just do this on a coarse mesh. So let's just assign the physical groups as well, because we'll need to tag the boundaries. So let's just add the physical groups. So I'll add a surface. So this is your surface 1. Is this appearing in the script? No, there is. Alright, so right, so this is my interior surface, and now this is the exterior surface. Let's also select a volume. So this is my internal volume, right? So 9 is are the interior nodes, 7 are the nodes on the interior boundary, and 8 are the nodes on the exterior boundary. So right, so this is our mesh, right? So now let's just export this. Let's just replace this guy. Okay, so now I'll just call this sphere 1, the same file which I just overwrote here right now, and so 8 is our exterior boundary, 7 is our interior boundary. So 8 is the exterior boundary, which I am calling as a wall. The inlet is the interior boundary, which is 7. So this is correct. All right, so now let's just solve this. And okay, so I just have to change the resolution. For some reason MATLAB doesn't work with, okay, right, so now you can see that this is the scatter plot, right? And let's just refine the mesh a bit. Let's just use refine by splitting. Right, so this is our mesh now, and let's just export this. Let's just replace this. And now since we are using a sparse assembly, we'll be able to solve this. So these were just 1000 elements, and let's just, now we have 84,000 elements, and these are 3D, but you can see that we can solve them really well. But now you cannot see the gradation inside, so we'll have to do this in ParaView. So here you have your right VTP file, which will export this to ParaView, and we'll see this how to do this in ParaView. But I have also provided a commented section here. So this is your post-process section, and you can also just define a parametric curve here and sample the solution along those nodes. And at each of those nodes, you just basically interpolate the solution. For that, first you have to again go to the element to node connectivity list, or rather the x coordinate. I mean the node, you have to extract the x values of your xyz values of your nodes, and then use your element to node connectivity. You must identify the element in which this point is present, and then just interpolate inside it. I'm sure there are easier ways of doing that, but really in this case we are using a linear solution, and in case of whether we do this on ParaView, it's really the same. So and really ParaView is much more convenient as well, so we'll just do this in ParaView itself. So alright, so let's open the VTP file. So this is my solution.vtp, my export. So this is my 3D plot in ParaView. Now let's just apply Delaunay 3D. Okay, so this is our surface kind of Delaunay kind of plot. So we'll just have to take a slice plot, take a slice, and let's just do it on the XY plane. So on the Z direction, I'll just define a unit normal as 1. Alright, so this will be my XY plane, and I'll just apply the slice. So this is my slice plot, and let me also add now the plot line, and we'll plot the solution along the X direction, so along the X axis. So let's just take point 1 as 1, 0, 1, 0, 0, and 12, 0, 0. Okay. Alright, so this is our solution, and now let's just export this and plot this against our analytical solution. So I'll just export this. So this is the export, and so now you can see these two columns here. This is your X coordinate, and this is your solution. So let's just copy these and plot it against this analytical solution. Right. So, all right. So let me just plot it once again. Okay. Right, so this is the comparison between our analytical solution and 3D FEM solution. So you can see that it is quite close, and of course we are using linear elements, so this is slightly off. If we use quadratic elements, then those tetrahedrons will really hug the spheres, both the inner and outer boundaries correctly, and the solution will improve quite a bit. So that's about it, and that's the extension to the 3D case. And you can see that this was very simple, and you could so really finite elements is you can understand that it's a very powerful tool, and now probably you can understand why it's so good for multiphysics. So we went from 1D to 2D to 3D by using the same kind of principles. And really, once you have a solver which is working for 2D, you can really extend it to any kind of 3D case. So it's not always so simple for other solvers, because you have to really take care of the boundaries correctly, and there are so many other features, like in your 3D case you can have complex boundaries, complex shapes. But in case of finite elements, you can handle all of these problems really easily. And that's really why finite elements are powerful. You can deal with complex structures. Again, you could basically do the same boundary integral by using our reaction forces, which we talked about. And you can see that we can just impose the Robin condition very easily by doing a boundary integral. So really this makes our life very easy. In case of maybe if you are simulating a reaction at the boundary of your electrode, for example. So in that case, you would have a Robin boundary condition at the electrode. If you were thinking of, for example, a wall function, which we also discussed in turbulent flow, you have wall functions. So those are also Robin boundary conditions. So you also have weak imposition of Dirichlet conditions, but I'm not showing it here because it's probably a bit more advanced. So that's about it. That's about the 3D case, and hope you can understand how easy it is to go from 2D to 3D. And in the next sessions, we'll look at Phoenix, which is really a very powerful tool. And this we'll do in Linux, because Phoenix has a lot of issues in Windows kind of environments. Sometimes there are some conflicts. So we'll just do this in a Linux environment. And you can see that our code, which was really sort of big for this case, right? Our shape function library, our solver, our driver, our post process. So all of these will become just very small lines in lines of code in your Phoenix. So let's just meet again in the next session, where let's start solving some nice problems on Phoenix. We'll also do some eigenvalue analysis, and also use those modes for creating a solution with reduced number of modes, right? Which is basically the analogy which goes towards ROM or POD, that is the reduced order modeling, right? So let's just do that, and in the next session we'll meet again, and let's start off with the Phoenix solutions. Thank you.